afternoon. My name is Yu-Hao. I'm today's presenter. I'm an undergraduate student from the National Taiwan University. Today, I would like to present the paper of our work, the development of a Gibbon-inspired Brachiation robot. My partners are Chen Bogang, Liu Guanjie, and Jing Lei, and our advisor is Professor Lin Peixun. My presentation will cover 4 sections: introduction, system design, simulation and experience, and results. So let's start with introduction. First, we want to ask why? Why do you want to build a brachiation robot? Well, speaking of this, I would like to quote a famous robotic design company, Boston Dynamics. They say, changing your idea of what robots can do. This is exactly what we try to realize. Nowadays, robots like humanoid could use various skills to achieve high dynamic motion, such as two-handed walk, run, or even backflip. So we think that by doing more research, maybe people could rely on these robots to do something that humans can't. So what is brachiation? This is a special move. This is a Gibbon-inspired behavior. So brachiation is a Gibbon's swing from one branch to the other. Why do they do this? Because to forage or escape from a threat. So here's a demo of Gibbons. Let's take a look.
Wow.
As you can see, this amazing creature gives a perfect demonstration of the brachiation. It's good. So we did some research on a related topic. Many researchers, such as Professor Toshio Fukuda, have already explored this field since 1991. And above these papers, we have found 2 characters. First is that they all define the whole Gibbons as a 2-bar linkage. The blue part is the arms, while the yellow part is the body. And the second character is that they only imitate the torque generated on the shoulder, which means that the brachiation use the energy accumulated on the shoulder, and the whole arm is regarded as a rigid body. However, we start to wonder, is it possible that Gibbons could do the brachiation only by the shoulder? In the previous video, we have seen that the Gibbons swing between branches with different heights. So we think that arm muscle might involve for grabbing the branch, because there is a pulling motion to grab. Furthermore, in the book Evolution of Gibbons and Stillman, the author has mentioned that Gibbons have strong flexor. What is flexor? Flexor, the muscle of the arm. And the strength it could provide is 3 times as many as Gibbons' weight. So it's highly possible that the arm muscle is involved and this pulling motion needs to be considered. So to imitate the muscle contraction, we take the pulling motion into consideration. This means that we need to add a new degree of freedom on the arm, which is a prismatic joint. In practice, we use the sliding mechanism to realize this concept. So our goal of this paper is to investigate whether this additional degree of freedom enhances the efficiency of the brachiation or not. So let's talk about how we build this robot. This is our brachiation robot. It has 3 essential mechanisms. First, this robot has 2 hook-shaped hands. The position where the hand touches the branch, we designed to be a passive joint. So the surface of the hand needs to be as smooth as possible to reduce the friction. Second part is the sliding mechanism, which I have mentioned in the previous section. We choose the quick return mechanism to realize, and its displacement is 10 centimeters. Here's a side view of our robot. As you can see, the brown part is a sliding mechanism, and the ochre part performs the rotation of the arm. So there's a question, how do we combine these 2 functions on a single arm? Well, we designed a coaxial system. Let me use an explosion map to explain. As you can see, the translation part is triggered by this motor, while the rotation part is with an additional belt. This belt transfers the power to the same axis with the translation. So we could then combine these two functions. So by these three essential mechanisms, we could therefore go through the experiment. However, before the experiment, we need some simulation to give us a primary instruction. So let's talk about our simplified model. We divide the gibbons into two parts, the arm and the body. The arm has two linkages, sliding part and a fixed part. And the last part is the body. One might ask, where is the feet? Here I want to know that we regard the lower half of gibbons as a rigid part. It's because while doing the brachiation, the gibbons actually crunch their body together. So it's unnecessary to separate them. And there are 3 degrees of freedom in our model, 2 revolute joints and 1 prismatic joint. And D2 is the stretching length of the robot, and theta 3 is the angle between the arm and body. But the most important parameter is the theta 1, as you can see. It's the criterion of the brachiation performance. The larger theta 1 is, the higher the robot swings. So, to build these degree of freedom with the input torque, we choose the Lagrange equation as our governing equation. Lagrange equation is the energy method based on ordinary differential equation. And there are 4 parameters affecting the whole equation. As you can see, K and U indicates the kinetic and potential energy of the system. In the lower half of our equation, capital theta refers to the state, which includes the 3 degrees of freedom and their differential terms. Last but not least, the input tau refers to the input torque on the shoulder and the input force for the arm. So we need control strategies to give the instruction. And this is the only parameters we could modify and implement our control strategies. So we need control strategy to enhance our performance. One for the torque generation on the shoulder, and one for the arm force generation on the arm. So let's start with tau 3. Tau 3 imitates the shoulder's torque. And we use a PD controller to track the theta 1. As for its target function, seems that the trajectory of theta 1 is supposed to be like a period function. Theta 1 should be swimming. So we choose a sinusoidal wave with natural frequency of the robot as a target function. Here we know that the more error occur, we need more torque. As for tau 2, the control strategy is similar but slightly different. Due to the robot's weight, we take the gravity into consideration. So we add a gravity compensation term here. And in the latter, the PD controller is still applied to track the D2, which is the stretching. As for the target function here, we use 2 cases to compare with, which is step point and the sinusoidal wave. The difference is whether this pulling motion is involved. If we use the sinusoidal wave, it means that it has a period function. So let's take a look about the results. This is a plot of the performance of theta 1. As you can see, blue line is using the set point, and the red line is using the sinusoidal wave. As you can see that the theta 1 rises from 8 degrees to 10 degrees. So we can therefore give a conclusion that the pulling motion, this additional degree of freedom, is effective in the simulation. So then we could move on to the experiment. So when we apply this target function into the robot, we have found that if we add another term, we could enhance the performance, which is the phase difference. Why? In the view of the biology, the phase difference represents the timing of muscle contraction. This means that if you use the right phase difference, it will enhance the performance, while the bad one will deteriorate. So we will then, but we don't know what value should we choose. So we will conduct experiments and return to the simulation for modification. Here's a demo of our experiment. First, we show a pure brachiation of our robot. And then we will apply sliding mechanism movements with two phase difference, right and wrong. As you can see, the motion of case 1 is enhanced. The whole body swings regularly while the theta 1 is larger than before. On the contrary, the motion of case 2, the whole body swimming pattern is destroyed and the theta 1 is smaller than before. And we could see the plots of previous results. The red line indicates the timing when the sliding mechanism is applied. As you can see, the theta 1 rise from 10 degrees to 15 degrees, about 30% enhancement. On the other hand, when we use the wrong phase difference, not only the peak value of theta 1 decreased, but also the swimming pattern is destroyed. It means that the robots couldn't reserve the energy for the next move. So we collect this experience result and return to the MATLAB to derive the best difference we could use. And we will generate new trajectories for both motors, the new control strategies. And so let's see what's the result after this modification. The two plots down here is the new trajectories for both motors for shoulder and arm. And you can see the performance of theta 1 rise from 10 degrees to 30 or even 40 degrees this time. It's a dramatically enhancement. So looking back to the goal of our project, whether this additional degree of freedom enhance the efficiency or not, well, I think both simulation and experiment give us an affirmative answer. The pulling motion will have a better dynamics. Furthermore, the timing of muscle contraction, we have found that this is also an important factor for the performance improvement. And these are our conclusions. It's an acknowledgement and our reference. This is my presentation. Thank you.